To understand biological life at the atomic scale, we must look at systems like the lipid bilayer membrane. This dense, multi-component structure dictates how cells interact with their environment, acting as a dynamic barrier and a host for countless proteins. Predicting how a system like this actually behaves, whether a membrane ruptures, a protein folds, or a small molecule passes through, requires knowing all the possible geometric configurations its thousands of atoms can adopt. To track these configurations, computational biophysics relies on the potential energy surface. Think of this as an abstract, multidimensional landscape where elevation directly represents the system's total potential energy. If you take every unique x, y, and z coordinate of every single atom in that lipid bilayer, that specific snapshot of the entire molecule maps to exactly one point on this surface. Molecular dynamics is the science of understanding how an atomic system navigates this invisible mathematical terrain over time. The potential energy surface itself is entirely static. It is merely a map of possible energetic states, plotting coordinates without any inherent motion. To turn this static map into a dynamic simulation, we have to apply differential calculus to extract mechanical forces. The system wants to slide down the energy gradients to reach stability, but a strict mathematical descent would simply freeze the molecule in the nearest trench. To counteract this, the simulation introduces thermal energy, random kinetic chaos that helps the system explore. These two competing engines, the downhill pull of mechanical force and the random kicks of thermal noise, dictate the physical reality of molecular existence. To see exactly how these engines operate, we have to build the potential energy surface from the ground up, starting with the simplest possible interaction. We will strip away the complexity of the biomolecule and reduce the universe to just two atoms connected by a single chemical bond. A simulation uses a mathematical force field to calculate the potential energy of this bond. We can plot this as a simple harmonic curve, mapping the changing distance between the atoms on the x-axis against their potential energy on the y-axis. If the atoms are pushed too close together, their electron clouds overlap. The resulting atomic repulsion causes the potential energy to spike exponentially on the left side of the curve. If the atoms are pulled apart, the system has to fight the attractive chemical forces holding the bond together, raising the energy on the right side of the curve. The lowest point of the curve represents the equilibrium distance. This is the most stable, lowest energy state for those two atoms. The massive potential energy surface of an entire cell is created by taking millions of these simple one-dimensional energy curves and aggregating them together. If we know the shape of this energy curve, how does the simulation mathematically force the atoms to move toward that equilibrium? The answer lies in calculus. The mechanical force acting on an atom is exactly equal to the negative spatial gradient of the potential energy. When the atom is stretched far from equilibrium, the slope of the energy curve is steep. The derivative of this steep slope translates directly into a large force vector pushing the atom downhill. As the atom slides to the exact bottom of the energy well, the slope flattens out. Because the derivative here is zero, the net force acting on the atom is zero. The simulation algorithm executes this process, calculating the derivative of the potential energy at every femtosecond time step to continuously update the position of every atom. Calculus provides the necessary mathematical bridge between a static, energetic geometry and physical Newtonian motion. As we add more atoms and interactions, that single 1D curve expands into a rugged 3D landscape filled with hills, valleys, and passes. The current state of the entire system is represented by a single point resting on this surface. A local minimum is a valley where the system is stable. The slope is zero in every direction, but the system is not yet in its most optimal, lowest energy state. The global minimum is the deepest valley on the entire surface. In biology, this corresponds to the thermodynamically ideal, fully folded state of a protein. Connecting these valleys are saddle points. These are the lowest energy mountain passes between two stable basins, mathematically representing the transition states of chemical reactions. Tracking the system rolling over a saddle point and descending into the global minimum reveals the exact mechanistic path of a successful reaction. The physical system always seeks the global minimum, but the rugged terrain is packed with local minima that constantly threaten to trap the molecule mid-process. Visualizing this as a 3D mountain landscape makes the math accessible, but it is a massive oversimplification. A real potential energy surface cannot exist in just 3 dimensions. Consider the math. A system contains n atoms. Each individual atom has an x, y, and z coordinate determining its position, which creates 3n dimensions. We subtract the 6 degrees of freedom required for the molecule's overall translation and rotation, arriving at the true dimensionality of the surface, 3n minus 6. This chart shows how scientists handle that complexity. Even a tiny 100-atom peptide has a 294-dimensional surface. To comprehend this, researchers project hyperdimensional data down into simplified free energy landscapes, like this one mapping bound and unbound states. Because the true topology of the system is invisible to us, the step-by-step mathematical calculation of the simulation algorithm is our only probe to navigate the darkness of this high-dimensional space. This introduces a structural paradox. If the calculated force gradient always pushes the system downhill into the nearest local minimum, how does a molecule ever climb over a saddle point to find the global minimum? The mathematical descent is counteracted by kinetic energy, defined in the simulation by the temperature variable, or kBT. This thermal energy acts as random vibrating noise. It continually kicks the system against the mathematical gradient, jostling the atoms out of perfect equilibrium. The probability of these random thermal kicks accumulating enough energy to successfully push the system over a high barrier is strictly governed by the Boltzmann distribution. Without this thermal noise, the simulation would instantly freeze at the bottom of the very first trench it encountered. Temperature is the necessary engine of exploration. When that engine fails to clear a barrier, we encounter the ultimate limitation of a simulation: broken ergodicity. Broken ergodicity occurs when the thermal energy of the system is simply too low to overcome massive energetic barriers. The simulation becomes permanently trapped, sampling the same irrelevant corner of the 3n minus 6-dimensional space over and over again. Overcoming this trap, ensuring the system thoroughly samples the relevant valleys of the potential energy surface, is exactly why modern biophysics requires immense supercomputing power, running for billions of sequential time steps. A molecular dynamic simulation is a single coordinate point dragged through a 3n minus 6-dimensional void, pulled by strict forces and violently jostled by thermodynamic noise. By mastering this mathematical landscape, computational scientists can calculate the energetic rules of molecular interaction, allowing us to predict the mechanical behavior of biological life from the bottom up.